अस्सलाम वालेकुम। ज़रा आना यार, ज़रा थोड़ी सी आवाज़ ऊंची करना। देखता हूँ। हेलो हेलो हेलो, ओके, ज़रा एक मिनट इधर ही देख लें। Alright, so today we're going to learn about one of the strangest phenomena of quantum mechanics, of modern physics, and that phenomena is called tunneling. So, but let me give you a motivation first. First of all, we've learned that in an infinite well, there are quantized energy levels, and the energy is quantized because the particle is confined on both ends. It's a bound particle, and we know that quantization is a result of confinement. Alright? And we also know that the wave function of the electron for different energy levels inside this well is given by the general form sine of kx, or sine of n pi x over L. So the energy is quantized, k is quantized, and if you notice, this sine of some function is in fact a combination of exponential functions e I n pi x over L minus e minus I n pi x over L. Right? This is another way of writing the sine function. Now this function represents a wave that is traveling from left to right, and this function represents a wave that is traveling from right to left. And when these counter-propagating waves, they interfere with one another, they lead to standing waves inside the infinite well. So we get standing waves, and so on. So now consider another scenario, in which the particle is not confined. The particle is free to move anywhere it likes. It's like a free bird. There is no obstacle that the particle sees. And the potential energy is zero everywhere. And the particle is injected from the left. So you throw in a particle, a photon, electron, neutron, proton from the left, and you give it a certain momentum, and it starts propagating from left to right. And inside this region, there is no barrier, there is no step. The potential energy remains constant everywhere, and it's in fact zero. So now what's going to happen is that this particle is going to propagate. This particle has some energy E, and this E is always greater than the potential energy. So all of the energy of the particle is kinetic. This difference is the kinetic energy of the particle. This is what we learn from classical physics. Now what we would like to do is, without solving the Schrödinger equation, we would like to write down what the wave function of this particle is. Alright, so we know that Eikx with some constant A, does this solve the Schrödinger equation? Yes, it does. B E minus Akx, does this solve the Schrödinger equation? Yes, it does. Therefore, their sum must also solve the Schrödinger equation. But this represents a wave that is a particle that is propagating from left to right, and this represents a particle that is propagating from right to left, because the signage here is negative. But is there any way that the particle that is thrown from left to right can reverse its direction and come back? No. There's no way that can happen, because the potential energy everywhere is constant. And if the potential energy is constant, we know that dV over dx is What's this equal to? 0. And it's equal to the negative of the force. So there is no force that is acting on the particle. If the particle has to revert its direction, it has to change its velocity, right? Which means it has to accelerate. Which means there must be a force that acts on the particle that makes it reverse its direction. So the particle changes its mind and can move in the opposite direction. But that's not going to happen here because the potential energy sees no change whatsoever. It's a flat landscape. Okay? There is no discontinuity in the potential energy. Hence, this B is going to be 0. So this term is going to disappear for this free particle that moves from left to right. Okay? This is the direction of increasing x. So mathematics gives you this solution. But physics tells you that, alright, mathematics, I respect you for what you've provided me, but physics tells me that this B has to be 0 because the particle is moving in a particular direction. Alright? So the wave function is given by this term. And if I would like to plot this wave function, it's a complex number. So mortal human beings have to plot either the real part or the imaginary part. Okay? I can choose any one that I would like to plot. If I plot the real part, it's just going to look like this. It's a sinusoid. And the imaginary part is also a sinusoid. One is sine and the other is cosine. I can choose any of these functions that my heart desires to plot this wave function. Now let's move a little bit forward. We have to go really fast today because right at 11 a.m. we also have a quiz. So this week's recitations and tutorials cover this aspect. Now suppose what's going to happen, a very strange phenomenon is lying, it's just around the corner. So hold your breath. Now the particle again is injected from the left and it moves towards the right. This particle, as you know, could be anything. Now here the potential energy is 0. And at a certain point in space, say at x equals 0, there is a discontinuity in the potential energy. Alright? The potential energy suddenly goes up. It's just like you're swimming in river Ravi and all of a sudden a muddy quagmire appears. So the swimmer is swimming in the clean waters of Ravi. They're not very clean, by the way, but suddenly the swimmer sees a muddy patch, a quagmire. Usko ek daldal nazar aati hai. So its energy is going to be expended in overcoming the friction. So likewise, a particle is moving freely in this region, okay, and suddenly it sees a barrier. The potential energy goes up. So some of its kinetic energy has to overcome the potential energy. So its kinetic energy must go down. Alright? Now suppose this particle is injected with an energy E. The vertical axis is the energy and the horizontal axis is space. And this height is V0. Now what do you expect classically? Can the particle penetrate into this region? Yes. Why is that? Because its energy is higher than the potential energy. Its kinetic energy is going to be reduced, but that's okay. Still the particle has enough leftover kinetic energy so that it propagates into this region. Okay? So now let's write down the wave functions. What's the wave function going to be in this region for negative x? I call this region 1 and I call this region 2. What's the wave function in region 1? Once again, I look at the Schrödinger equation, I get these two terms. A E I K X plus B E minus I K X. First question. Is B going to be 0 here?
No.
आपका क्या ख्याल है? B 0 नहीं होगा, क्यों नहीं होगा?
B नोट ज़्यादा है लेवल से, पहले 0 थी अब B नोट.
Right. So there is a discontinuity in the potential energy, which means that this particle is effectively seeing another medium here. Alright? There is a discontinuity in the potential energy, which means there has to be some force, conceptually some force that is acting on the particle. And when there is a force acting on the particle has to accelerate. And acceleration means a change in velocity, so it can change its velocity and it can in fact reverse its velocity. Okay? So the particle can bounce off from this edge and it can move in the backward direction. So there has to be a backward propagating wave as well, and therefore this B is not going to be 0 here. Alright? Now what about this region? Let's write down the solution of the Schrödinger equation. I have CEI K dash X plus DE minus I K dash X. Can you tell me if this D is going to be 0 or not? Yes, it's going to be 0, because once the particle has entered region 2, there is no obstacle that it sees towards its right, so it cannot reflect back from anything in region 2. So this term is 0. Alright, now what about these values K dash and K? This K of course equals K square equals 2me over h bar squared. This is a result of the Schrödinger equation, and this you should all know how to get this K squared. And this K dash squared equals 2m over h bar squared, and what should I write here? E minus V naught. This is the excess energy of this particle over and above the potential energy. Now could you please plot the wave functions? For example, just the real part in these two regions. आज के क्विज में इससे भी आएंगी चीजें. That's fine. EIKX आगे माइनस ओमेगा टी है ना, तो ये मैं क्लास के बाद बताऊंगा. ठीक. So what's going to happen here is, here the wave function is oscillatory, right? There is some wavelength, and which K is larger? This one is larger, this one is smaller, hence the wavelength is going to be smaller in region 2, larger. Wavelength is going to be larger. So this is a plot, an approximate plot of a sketch of the wave function. That is just by chance. G. I've answered this question quite a few times, but let me answer it again. K dash is decreasing. K dash is decreasing in region 2, which means the momentum is decreasing, which means the speed of the particle is decreasing in this region, which means that if you would like to localize the particle and see where it is found, it's moving with a slower speed, so it's a higher probability that you will find the particle here. In other words, this coefficient C is large. This coefficient C can be large. So when the particle is moving slowly, in general, the amplitude goes up. Just like the musical chairs analogy. Alright, now what we are observing here is something which makes classical sense as well. Remember, we're going to move on to quantum devices. So this is the stepping stone to understanding some important quantum devices. So please pay attention, especially the people at the back. The particle has some energy. This energy is sufficient to overcome the potential energy. Excuse me, I will not let you sit in the class. You're fiddling with your phone. So the particle has some energy, and this energy is sufficient to overcome the potential energy. Therefore, there's nothing stopping the particle. There's nothing impeding the particle. The particle has to move on. But there is a strange surprise that you're not observing, which is not evident to you, and that is the presence of this term. This term means there is some reflection. So even though this particle has an energy greater than the potential energy, the particle still has some chance of being reflected. Now if you look at this scenario, I can define a transmission probability. And denote it by capital T. What the transition probability means is the following. If I have a single particle, a single electron or a single photon, and it is ejected from the left, it enters this landscape, then there is a probability that that particle can be reflected from this discontinuity. Alright? And there is a probability that it can go into this region. There is a probability of reflection and a probability of transmission. Alright? Even for a single electron, a single photon, just like a beam splitter. Now if I would like to define a transmission probability, what I would like to do, I would like to make a plane in this region, and I would like to make a plane in this region. So this is just a hypothetical plane or a screen, a permeable screen जिसमें से particle गुजर सकता है, and I find the probability per unit time that the particle crosses this screen and goes from left to right. Right? So, and then I find out the probability that the same particle crosses this screen going from left to right. So I have this plane and I have this plane. I look at a particle, the particle crosses this plane, alright, which is a measure of the incidence probability. And then the same particle crosses this plane. I divide the probability of the particle crossing this plane with the probability that the particle crosses this plane. I'll find the transmission probability. Agreed? So how do I find the transmission probability? So let's call this plane small a and let's call this plane small b. The transmission probability is defined as probability that the particle crosses plane B per unit time divided by the probability that the particle crosses plane A per unit time. Alright, so this is the transmission probability. Is this a reasonable definition? Right, it makes sense. It's a reasonable definition. Now the probability per unit time, any probability per unit time is given by probability per unit length multiplied by length per unit time. Agreed? So what is probability per unit length? This is just the modulus squared of the wave function. And what is the length per unit time? This is just the speed of the particle. So what I would like to do, if I would like to find the transmission probability T, in the numerator I have the probability that the particle crosses B per unit time. I take this wave function, and what's the incident part of this wave function? This term, A. So I take the modulus squared of this part. That will give me A mod squared. I have to look at the what happens to this first. So what should I write here? What is the probability per unit length? It's C mod squared. And what is the speed of the particle? It's just this. This is, I can find the momentum, right? The momentum P is given by h bar k. So the speed is given by h bar k over the mass of the particle. So in region 2, the velocity of the particle is simply h bar k dash over m, where k dash is given by this. And what's in the denominator? I look at the probability that the particle crosses plane A per unit time. So which wave function do I choose? I choose this wave function, because this represents the particle propagating from left to right and crossing this screen. So I take the modulus squared of A h bar, the speed is h bar k over m. So the transmission probability is C mod squared k dash A mod squared k. This is the transmission probability. The probability that a single particle impinges onto this step, with what probability does the particle move ahead? And what's the probability going to be for the particle to be reflected? It's just going to be 1 minus t. So R is going to be 1 minus t. समझ आ रही है सबको? स्पीड क्या है? स्पीड भी तो लेनी है ना. स्पीड इज मोमेंटम ओवर द मास.
लेंथ ओवर टाइम के लिए स्पीड.
जी जी अब्दुर्रहमान नवीद. So we define transmissivity or the transmission coefficient. Please stop talking. Please stop talking. We define the transmission probability as you have an incident wave. What's the probability that that wave propagates ahead? So you look at what goes into region 2 and you compare it with what is incident. So what is incident is the A term, and what goes ahead is the C term. Alright, so now let's look at the value of A, B and C. Now we have to find out what C is, and we have to find out what A is. How can we do that? We look at the boundary conditions. And what is the boundary? Where is the boundary? It's at this point, x equals 0. So at x equals 0, this wave function must be equal to this wave function. So at x equals 0, now what is this wave function at x equals 0? What's this term equal to? आप बताओ, आप जी आप बताएं. A. And what's this term equal to? B. So at x equals 0, I have A plus B equals the this wave function at this point. And what's this wave function equal to? C. So this is one of my constraints. And what's the other constraint? I take the derivative of this and find the derivative at this boundary point. I take the derivative of this and find it at the boundary point. Both of them must be equal. So if I take the derivative of the wave function in region A, I get ik A minus B. This equals ik dash C. Just convince yourself that what I've written in this part is correct. Just convince yourself. Half a minute. ठीक है, ये समझ आइए? नहीं आई?
क्योंकि सर वो दोनों ऑपोजिट डायरेक्शन में जा रही हैं तो उनकी ग्राफ्स भी ऑपोजिट डायरेक्शन में होंगे.
डिफरेंशिएट किया.
ग्रेडियंट सर जब उनको प्लस करेंगे तो एक नेगेटिव है एक पॉजिटिव है तो लेसर वैल्यू आएगी.
ई आई x equals 0 पे वो 1 हो जाता. Alright, so if I would like to compute the transmissivity, I have two equations. I need to eliminate B. Okay, so this I just cancels out and I get A minus B equals K dash over K C. So I add equation number 1 and 3. The B cancels out, I get 2A equals C1 plus K dash over K. Let's call K dash over K as beta. Beta is, I just define K dash over K as beta. And as you can recognize, this is just equal to E minus V naught divided by E under root from these expressions. Alright, so now I have 2A equals C1 plus beta. This means A is C over 2 1 plus beta. This means the transmissivity T is going to be C mod squared into K dash divided by A mod squared, which is the C mod squared 4 1 plus beta squared K. This is 4 K dash over K is beta. So this is my transmissivity. Just think over it first.
Let us digest.
Just digest this. Think over this first. This one? I just add 1 and 3.
You took K dash over K as beta?
Yeah. ये हमने डिफाइन किया इसे and it makes sense. Does make sense, right? You look at the particle that is crossing screen B per unit time. That is the transmitted particle. And then you compare it with the incident particle, and that particle is the one that crosses screen A. जी wave function has to be continuous. That's a property of the wave function. The wave function has to be continuous, its derivative has to be continuous. Alright, so this is the transmission probability. If I have one particle, the probability that this particle is going to move forward is this much. If I have 100 particles that strike this potential barrier, then 100 times T of those particles will be transmitted. Alright? So quantum mechanics works with one electron, with one proton, with one photon, and it works with large number of photons as well. Large number of particles. Now what I would like you to write on your notebooks after some intelligent thinking is how do we define R? Write an expression analogous to this expression, the reflection coefficient. उसके analogous लिखो.
Aside from 1 minus T.
Yeah. शाबाश. इसमें ऊपर केस नहीं आएंगे, कैंसिल हो जाएंगे. शाबाश, वेरी गुड. इसमें केस नहीं आएंगे, कैंसिल हो जाएंगे
क्योंकि वो इक्वेशन में एच फैक्टर दोनों में सेम के है.
के सेम,
जबकि उसमें के प्राइम था, सिर्फ काट.
Alright, so that's very good. Students have a fair idea of how to define the reflectivity. That reflectivity is simply B mod squared into K over A mod squared into K. This K just cancels out because both the incident and the reflected waves, they are in the same medium. And then you can find out, you can eliminate C from those equations, and you'll find out that an expression for R, and later you can verify that R plus T equals 1. Now the strangeness of quantum mechanics is slowly making its presence felt. Suppose I have a potential landscape that looks like this. This potential energy is 0 here, and here there is a drop in the potential energy. This drop is V0, and a particle comes in with an energy E. Is the particle going to be reflected at this discontinuity?
Second equation दी
ये derivative को बराबर रखा है. Okay, first answer my question. Is the particle in quantum mechanics, is it going to be reflected? Yes. So quantum mechanics does not care whether the potential energy goes up or down. If there is a discontinuity in the potential energy, there has to be some analog of the force acting on the particle, which makes it reflect. So this is something strange. Both of these effects are in fact equally strange. In this case, the energy of the incident particle is greater than the potential energy. Still the particle can be reflected, even though classically all of it should propagate into region 2, because there is nothing that is stopping the particle. Here it's even more surprising, because the energy of the particle is greater than the potential energy, and if anything should happen here, its kinetic energy should actually go up in region 2. But despite an increase in kinetic energy, the particle can still be reflected because there is a discontinuity in the potential energy. Okay? It's just like having a pool of water. You have a pool of water, and you have a cricket ball, and this cricket ball is thrown with a certain energy into the pool of water. Suppose this cricket ball has an energy of 50 joules, and this pool of water represents a potential barrier of say 20 joules. The classical prediction is that this ball should actually enter the pool of water with a reduced kinetic energy, and inside this pool of water, this ball is experiencing some viscous force and its energy drops, because 20 joules of its kinetic energy is used in overcoming the potential barrier, and the remaining 30 joules is the residual energy of this cricket ball. But it enters the pool of water. There is no chance for this cricket ball to be reflected and bouncing off from this pool of water. But quantum mechanics tells us that if this were a quantum cricket ball, which we call an electron or a proton or a photon or a neutron, then there is a finite probability for this quantum object to be reflected from this surface. Okay? Suppose I have air here, and here I have glass. A beam of light that comes in from air can be refracted into the glass, and some of it will be reflected. Now the refractive index of glass is higher than air. The speed is lowered inside glass of light. Likewise, if I have light traveling inside glass, the finite probability, it sees an interface, a discontinuity in the refractive index, it can be reflected, and it can also be, a portion of it will be transmitted. So a single photon that sees an interface is a probability that it will be reflected and a probability that it will be transmitted. Okay? So it is surprising, but not so surprising when we look at refraction. Now let's look at another very interesting aspect. A really strange aspect, which makes quantum mechanics look like a horror movie, because things get very strange, very spooky, very eerie when we discuss this. Alright, so now what's going to happen? The energy of the incident particle is smaller than the potential energy, and the particle is injected from the left and it's moving rightwards. So in region number 1, of course its wave function is going to be A, E, I, K, X, plus B E minus IKX, because there is some reflection of this particle. What's going to happen in this region? What does classical mechanics tell you? Can the particle penetrate into this region? No, because it's just like having a quantum rabbit or a rabbit inside a valley. He has to surmount a hill, and the potential energy that he has to muster is 900 joules, but his own energy is just 80 joules. So classically, there is no chance of finding the particle in this region. The particle cannot penetrate into this region, so the wave function has to go to 0. However, that's not the case. If you look at the Schrödinger equation in this region and solve the Schrödinger equation, which I've done in the previous class, I can come up with a wave function which looks like this: C E minus alpha x plus D E plus alpha x, where alpha squared is 2m v naught minus E over h bar squared. So this is something we derived in the previous class. Now there is no iota here. One thing, there is no iota here. Alpha is a positive number. Alright, it's a real positive number. So this is the total wave function that mathematics provides you, the Schrödinger equation provides you. Can you tell me something about this term? When x goes to infinity, what's going to happen to this term? It's going to blow up. It's going to go to infinity as well. But the wave function cannot be infinite. Okay? So mathematics tells you that, okay, this is a legitimate solution. This is a solution. But physics tells you, okay, thank you very much, Mr. Mathematics, but I can't trust this because this is going to blow up. This is going to mess up all of my physics. Because then the particle is always going to be found at infinity, because the wave function is going to infinity. So I have to put this equal to 0. So this is the wave function in this region. And if I would like to plot what the wave function looks like, it's oscillatory here. It has a certain k. K is just given by 2me over under root over h bar. So it's oscillatory here. K remains constant in this region. And when it touches the boundary, it's going to decay exponentially. So it's going to decay, it will go to 0 very quickly. G. The wave function does not become discontinuous. This is not a discontinuous function, it's a continuous function. No, the derivative is finite. The derivative is not suddenly changing. हाँ तो एक्सपोनेंशियल का डेरिवेटिव भी कोई ना कोई होता है, लेकिन यहाँ पे इस बाउंड्री पे द डेरिवेटिव इज नॉट सडनली चेंजिंग. डू द होमवर्क. Okay? So what's going to happen here? The wave function, even though the energy of this particle is less than the potential energy, the wave function is going to dip. But it penetrates a small length into this classically forbidden region. This region is classically forbidden. Sir Isaac Newton would tell you that no, it's not possible. But Schrödinger, Mr. Erwin Schrödinger tells us that it's possible to find the particle in this region. Because the wave function is small, it's going to 0, but it does not start off with 0. There's a finite probability of locating the particle here. Now how do we verify this fact? Suppose I change this landscape a little bit. Okay, now here the potential energy is 0. here it's V naught, and here it's 0 again, and the energy of the incident particle E is less than V naught, and this length is L. Let me first tell what's going to happen. Still transmission is going to occur if V naught is exactly equal to V naught. So just imagine that Mr. Bilal Ayaz, our famous Mr. Bilal Ayaz, is standing outside, right? And I'm standing inside. And what's happening here, there's no door to this auditorium. Now I have a certain amount of energy, alright, because I've had a good breakfast, so I've increased my chemical energy. I have a certain amount of energy. That energy is, of course, is coming from the glucose inside my body. So I have kinetic energy. Now what I would like to do, I would like to walk towards the wall and suddenly shake hands with Mr. Bilal Ayaz. But Mr. Bilal Ayaz is on the other side of the wall. So I do not have enough energy to penetrate this barrier. It's masonry here. This wall is representing a potential energy barrier, an obstacle. But Mr. Bilal Ayaz is anxiously waiting for me, standing outside, because I want to shake hands with him. So quantum mechanically this is possible. This is possible if this wall has a small width, and if I have enough energy, even though not enough energy to overcome the energy barrier, but still I have some energy that is close to V naught, or this length can be reduced. So this phenomenon is called quantum mechanical tunneling, and it really happens. So what's going to happen in this case is that we know that the wave function here is going to be A e I kx plus B e minus I kx. So it's going to be oscillatory. Inside this barrier, I will have a wave function of this kind, because the potential energy is now higher than the energy. So I will have a kind of decaying function. I will have this term, but I will also have this term, because my x is not really going to infinity. This is x equals 0, this is x equals L. So my x is not really going to infinity, so I will have this term as well as this term. And the combined effect of these terms is that this wave function is not going to be oscillatory. It's not going to wiggle up and down. Rather, it's going to decay. It's going to decay very fast in distance. I mean, it's going to decay to very small amounts in very short lengths. But when I reach this barrier, if this wave function has not completely decayed, if this wave function hasn't completely decayed, which is possible when this length is small, then some of the energy that reaches this point can leak off onto the other side. And then I will have a wave function with the same wavelength, with the same k value as the k value here, but with a much reduced height, the much reduced amplitude. So what this means is that if I have such a situation, and your homework looks at this question in more detail, if I have a situation where an incident particle has energy less than the potential barrier, then all of this becomes classically forbidden. But quantum mechanics tells us, by solving the Schrödinger equation, that some of this energy can leak into this classically forbidden region. And if you see a photon here, if you see an electron here, it means that that photon must have penetrated through this region. This phenomenon is called quantum mechanical tunneling. एंड इट्स नॉट, ये कोई किताबी फिनोमिना नहीं है तो सिर्फ किताबों में मिलता है, ठीक है, ये कोई अलिफ लैला की दास्तान भी नहीं है, ठीक है, which is just fictional. In the next lecture I will give you 3 examples of quantum mechanical tunneling, but let me first of all give you a demonstration of tunneling with light. I have to be very quick, so if you're really restless.
Is L a function of the wavelength of?
No, L is just the material itself, how big the barrier is.
Threshold value, is it a function of
L is provided to you. All right, let's look at this example. इसको on कर दो. देखिए, I have to move on, I'm sorry. Okay, let's look at this example. We have glass and we have air. Do you know what the phenomenon of total internal reflection means? Yes. When does total internal reflection happen? बात सुनो ध्यान से, कब होती है टोटल इंटर? जी, when is transmission zero? So if you have a photon inside glass or a light inside glass, and this photon hits a barrier with another material like air which has a smaller refractive index, then some of the light is reflected and some of the light is transmitted. If I increase the angle of incidence, the transmitted light increases in intensity and the reflected light goes up. Eventually, if I reach an angle of incidence greater than a critical angle, which depends upon the refractive index, all of the light is reflected. Okay, this is called total internal reflection. Now what's happening here is a photon is inside this medium and the photon is seeing a barrier here. Now the photon does not have enough energy to overcome this barrier, so all of the light is reflected. So this is just like this case. It appears that a photon is inside glass, it sees a barrier and the photon is totally reflected. Okay, but what quantum mechanics tells us is that this photon must have a quantum field which leaks off into air. Okay, which leaks into air like this, some quantum field that leaks off into air and it damps very quickly. It does not go far enough into the air. It damps very quickly because the damping is exponential. Alright, this is what quantum mechanics tells us. But we can't see this damped field. So what we would like to do is we would like to place another glass medium. This is again glass. We would like to have another glass medium brought very close to this interface. Okay, extremely close to this interface, such that this glass medium is within the penetration depth of this leaking field. And if this glass medium is brought really close, then this reflected light will decrease in intensity and you will see a transmitted beam. It could be a weak transmitted beam, but still you'll be able to see it, because we have now tunneled the photons out of this region into a neighboring region. So this is optical tunneling, and we have what is called frustrated total internal reflection. This phenomenon is called frustrated total internal reflection. optical tunneling. Now I have a small demonstration for you to show you this effect. इसको ऑन करूँ यहाँ से? ऑफ करूं? बिल्कुल बंद हो जाते हैं. ठीक है, एक मिनट. Let me just. All right. So what we are seeing on the screen right now is I have a laser light. It's green colored laser light, and this laser light is coming in from here, and this is a prism. So this is a glass prism with a certain refractive index, and the refractive index is such that the critical angle is about 42 degrees. So this laser beam comes in, and the angle of incidence is the angle with the normal to this plane, and it's about 45 degrees. So the angle of incidence is great. This angle between this normal and this incident light is greater than the critical angle. Hence, total internal reflection takes place, and all of this light is reflected. Okay? So it's a green laser. It is shining on a prism. The light is reflected and goes here. But quantum mechanical tunneling effects tell us that some of this light must also leak off into this classically forbidden region. However, if I take another prism and I place it close to the first prism, now here I placed another prism. No light is actually transmitted. Okay? So I move this prism closer. No light is transmitted. So if I would like to tap off light, I would like to pick off some light. ठीक है ना? हम लाइट को पिक ऑफ करना चाह रहे हैं. उसको बहुत डेलिकेट लाइट है, बहुत डेलिकेट इस लिहाज से कि इट्स इवेनेसेंट. This light that goes out of this prism is called evanescent light. Evanescent का इंग्लिश में मतलब समझते हैं? Evanescent का मतलब इंग्लिश में है जो भागने के लिए तैयार है, बहुत ही नाजुक, यानी भागने के लिए तैयार है. It's very difficult to capture this light. In other words, उर्दू में इसको कहें गुरेज पा, वो ज्यादा मुश्किल है. तो ये इवेनेसेंट लाइट है, और इससे इनफैक्ट माइक्रोस्कोपी करते हैं इस लाइट से. आप बायोलॉजी लैब में जाके पूछना. तो if I would like to capture this evanescent light, this prism has to move really close. But I cannot capture this light, because if I would like to capture the evanescent light, the length L has to be of the order of the wavelength of light. That's about 500 nanometers. So I can't capture this light. So I cannot verify for sure that I'm frustrating the total internal reflection. I know from mathematics that tunneling is happening, but I cannot capture the evanescent light. So what we've done instead is we've made another arrangement. Now what I'm going to do is I'm going to place two prisms back to back, and those prisms have been joined by a fluid, by an adhesive fluid, so that the distance between those prisms is less than a micron. Right? So I'm within the penetration length of the light. So I'm able to pick off the evanescent light and frustrate total internal reflection. So I have two prisms. Still it's not one prism, it's two prisms joined back to back with some fluid, which makes the two prisms adhere to one another. and I would see that total internal reflection has been frustrated and I get transmitted light. Bismillah. All right. So what we see here is, this is the original prism. Light is coming in from here. It's now you can see that total internal reflection has been frustrated, because I put in another prism and I placed this prism close enough to the first prism that the gap between these prisms is of the order of a wavelength. It's about half a micron or less, because I've used some special fluid to conjoin the prisms. Still, there are two prisms and there is a minute gap. You can never make the gap go to zero. So some of this incident light, when it reaches this interface, it actually tunnels off into this medium. This medium is identical to this medium. There is a gap in between, and the total internal reflection has been frustrated. As you will see here, even here, the angle of incidence is still greater than the critical angle. Therefore, classically, you would expect only total internal reflection to occur. But you see a transmitted ray here, right? Light is being transmitted ahead. This point is just a reflection of this point, so don't worry about this point. This light is being transmitted straight ahead. So I have frustrated total internal reflection. Previously, all of the incident energy was going here. Now this energy is diminished and a large portion of the energy is actually being transmitted. This light is being tunneled from this across this barrier, even though it was not allowed to do so. But quantum mechanics tells us that this total internal reflection can in fact be frustrated. So this is the best visual demonstration I can give to you of frustrated total internal reflection and hence optical tunneling. In the next lecture we look at 3 devices that use quantum mechanical tunneling. And now welcome to the quiz.